Another key component of any turntable is, of course, the cartridge. The cartridge is where the energy is being generated in the system. And of course, if that energy is not controlled, then the first thing that happens is the rest of the structure that is associated with the cartridge, i.e. the tone arm, also becomes excited in sympathy with what the cartridge is doing. Even the stiffest tone arms in the world still start to resonate in the region of 6 kilohertz. So it is important when one looks at the design of a cartridge to consider the idea of trying to raise the specific stiffness of the cartridge assembly so that its first resonant frequency is the highest possible. Now, in order to do that, we have applied again selective laser sintering technologies using titanium as the base material. So in the cartridge we see here, which is called the tessellate because of the structures that we've created in the system to create the high specific stiffness, we have not only the cartridge body, which is a U section, but we also have what is called the fin. It's the combined impact of these two systems that elevates the specific stiffness of the head shell and the cartridge to a level that was previously impossible. The titanium is also very important because it has no interaction characteristics with any magnetic fields, unlike aluminium, for example. So the titanium is not only the best material for this particular function, but also it provides the facility to enable this added fin structure that enables the system to become much stiffer at the point where the energy is being generated. So what we have here in the tessellate system is a very, very high specific stiffness, but also, as a result of the cork interface between the fin and the head shell of the cartridge, a very highly damped system. We also augment that damping using a viscoelastic adhesive. So when you look at this system, it's not just simply bolted together, because what we also introduce is a viscoelastic damping mechanism between the cartridge and the head shell. Now, because of the tessellated structure that is built into the titanium, that means that the viscoelastic adhesive that is used to bond the cartridge to the head shell also creates a very intimate interface between the two components. Typically, when you look at anything that is being joined together, you will only get 3 actual contact points, like a 3-legged stool. Therefore, it's impossible to legislate usually where those 3 contact points are on the conventional head shell cartridge interface. With the tessellate cartridge, what we have with the adhesive layer is a complete control over that interface, which means that we are controlling as best as we possibly can what is happening with the energy that's coming from the cartridge. Another key part of this cartridge design is also to be found in the cantilever itself. So for the first time we have what is a hybrid cantilever. We have cartridges with boron, sapphire and diamond, but on the cantilever itself, which is obviously the first place where resonance is going to occur, we have also added a UD carbon sleeve to the cantilever itself. Now what this does is it adds stiffness to the cantilever, but it also adds damping to the cantilever. So for the first time, the characteristics of the cantilever are not so clearly obvious in this cartridge. It's a characteristic of all cartridges that one can easily determine whether it's a boron cantilever or a sapphire cantilever, for example. However, with the addition of the carbon fibre, we have been able to damp and control the effects of this characteristic more than ever before. So the performance of the tessellate cartridge is quite different to anything that you will have heard. It's a completely different approach, not only in how the cantilever works, but also in terms of how the body of the cartridge works in relationship to the head shell. It's quite unique and totally novel.